Hi, Bill and Lonnie. For everybody else watching this, I don't care if you watch or not, but this is a temporary video meant for Bill Thomas and Lonnie Robinson to show them something, and then I'm going to take this offline afterwards. So, anybody else that's subscribing, this might be boring. All right, so Bill and Lonnie, I'm going to show you my ATF Hartmann. So, I think my screen's working. So here's what I got. This is a display and data sheet, or data display sheet. And I got another sheet where I got all my arithmetic. So for right now, I'm just going to stick to the data display sheet. So when you start the ATF Hartmann, you only enter in yellow fields. So this are zones from SIT and Easy Hartmann masks. That's zone 76543. I don't have a zone 2 or a zone 1. Secondary mirror's in the way. So instead of having all those holes, I have only got 40 holes that are going to be put into the sheet. So I can go ahead and make the sheet so that it inputs these holes from your guys' mask holes, but right at the moment I just input the radius, the radii of the holes, and I may change that later. All right, right here you put in the name of the mirror. So this could be Bob Jones right here. And the next one is the optical aperture, not the physical diameter. Then the radius of curvature, the size of the holes. It then computes the focal ratio. I put in the date. I put in the photo number. I put in pixels per inch on my CCD. So my EOS has 5,905 pixels per inch. And this is how far inside of focus I want to intercept my dot pattern with a examination plane. I then shoot the image in the telescope at Polaris, run it through image J, do the same old song and dance. I get the centers of gravity to 3 decimal points after the decimal, and I make sure that I click to eliminate scale. And then I input these 40 data points into this yellow field here. So this is the X and Y positions of these whole numbers. Alrighty, so at this moment I then have, before I go on, the size of the mirror is transferred from that cell. The focal length of the mirror is transferred from this cell by dividing it by 2, and the focal ratio is transferred from, where is it? That cell right there. Okay, so I have 2 displays right now. I'm going to have another display later, but right now I have 2 displays. One is the dot pattern of this plane crossing the optical path orthonormal to the optical axis. And then I have an astigmatism evaluation. So I'm going to start with the astigmatism evaluation. On zone 7, I have 4 axes. The dot patterns, these numbers here is how far it is from that dot to that dot on the CCD in pixels. And then I have it color coded so that the biggest one is green and the smallest one is red. And the difference between the biggest one and the smallest one is displayed here. And then I have taken that number and divided it by the first one in the box. Since they're all really close to the same, I just took that number, divided by that number, and entered it here. So Lonnie is thinking that 0.5% is already too big. So as you can see in this one here, it's 0.8%. So it's color coding it as orange. If it were 1% or more, it would color code it as red. So if it's between 0.002 and 0.005%, then it changes it to yellow. So yellow is technically acceptable, we think. If it's smaller, it turns green, and if it's smaller, it turns deep green. So the greener you get, the less astigmatism each zone has. So I got a process for zone 7, process for zone 6, 5, 4, and 3. What I'm hoping for is that these percentage numbers will match Lonnie's easy Hartmann percentage numbers. They may be off by a factor of 2 because we're at the focus instead of the ROC, but I think it ought to be the same ratios if our tests are both valid. Anyways, so this quick check tells me I'm free of astigmatism when these guys are yellow, better if they're green, and fantastic if they're deep green. And then if I want to know which one is longer, it would be the shorter of these numbers, because the more they spread, it's as a result of having crossed sooner. So the wider they spread, the shorter the radius of curvature. So this green one is a short radius of curvature. I'll come down this one. This green one in zone 6 is the short axis, and the red one is the long axis. So I now know color-coded. Sorry, Lonnie, I guess you're colorblind. Sorry. The color coding tells me which are long and which are short, and these boxes tell me by how much. So technically, if these guys here are 0.005 or smaller, I technically will not care about those guys over there. Okay, the other display is my dot. So this is, I'm using plane of intercept, and I've got this 1 here. That means I'm 1 inch before focus. So that's 1 inch on the mirror side of being through the focal point. And these are the dots. So you can tell which dot comes from which zone. So my plan is I will make the mirror so that they have this illusion, and then I can come over here and I can get closer. So I can go to 0.7. And as I do that, the scale changes, the dots scoot around. As you can see now, the zone 7, at least on radial 1 and 8, are further from the other dot. So we can tell there's a correction malfunction there. Now that correction malfunction ought to collaborate with the easy Hartmann range 1 and range 8 zone 7 issues. So let's say I can work the mirror here until they're good. And then I can get a little closer. Let's come over here and go 0.5. And now you can see it's still looking like that. By the way, this is not a good mirror. This is, as you see, this is a crappy mirror. I'm going to go to 0.2. And by the time I get to 0.2, those zone 7s in radials 1 and 7 and 8 are really starting to diverge from the others. And so if I go a little closer, you can see that they really start to diverge. And of course, we're still way the heck outside of where we want to be. So let's come over here and go 0.02. All right, now they're all scattered out. So when you're this close on a crappy mirror, at this moment, just by looking at it, you cannot tell which dot goes with which radial or which zone. Now, if I put my mouse on it, it'll tell me where it came from. But the bottom line is, before I get to this point, I'm going to spread that back out to 0.06. Let's go a little further. Let's go to 0.1. All right, this point, you can still tell where they come from. So I would work the mirror at this point until they look better and then move in. So if I keep moving in while they're still in the right order, I won't lose track of where they come from. Now the idea is I ought to be able to go down to 0.001 and just keep on going and going until, theoretically this just keeps being in the right positions all the way. But what's going to happen is when I want to get really small, like 0.001. Let's go to 1,000th of an inch inside of focus. You can tell I got a real problem here. Now my area disk is 0.0001. That means my area disk is only, I don't know if you can see the screen now, it's only about that big. Of course, these dots are all outside the area disk. But what my plan is, as I work the mirror, as I'm getting in closer and closer and closer, I'll be able to keep going until all these dots are falling within the airy disk of the optic here. So one thing I want to do is I want to add a red circle that's the size of the airy disk onto this dot pattern. I do not know how to do this, but I'm hoping that somewhere along the way, one of you smart guys is going to show me how to do that. So if you just look at this mess, you're never going to be able to figure the mirror from that. So you literally are going to have to start, at a further, see that? See if it's too far. Let me come back here. I'll go really big here, 0.5. Okay, you know which one goes with which one. As you get closer and closer, you should be able to tweak the mirror and keep them in order as you get smaller and smaller and smaller. Now, my hopes is after the mirror has been easy Hartmann tested on all 8 radials, I'll be able to go into a very close examination and know which is which. And my goal is to finish a mirror. So all these dots are hopefully crisscrossing each other inside the airy disk, maybe even really close to the center of the airy disk. I know these are raised, not wave fronts, and you can't really make a Strudel ratio adjustment on that. However, it makes sense that not only should all these dots go through the airy disk together, but hopefully compacted in the center of the airy disk. I should be able to get this thing to 0.0001, really close. The airy disk will show itself really big, and those dots will still be really tight inside the center. If I were to go on the other side of focus, those dots would pass through. I'm going to go negative 0.5, should pass through and exchange sides. And so there's what it looks like outside. And as you can see, the error over here is now switched to this side, and the error over here is now switched to this side. So instead of 7 and 6 being far apart, they're now close together. What?
What time do you want to eat?
I'll be in 5 minutes. I'm recording right now. I'll be in 5 minutes. Okay, so the zone of range 1 and 8 were spread apart when I was outside, or when I was inside of focus, and now they have switched to the side. So this is the zone. This is range 1, and this is range 8 outside of focus. And notice they are closer in. So it makes perfect sense that if you're too far out, too far spread apart inside, you'll be too close inside. I want to show you one more thing on here that I like. So I'm going to get inside of focus. I'm going to go kind of close. All right, well, let me go a little closer. There's something I want to show you here, so bear with me. I know this is boring, but bear with me. Yeah, I'm going to have to go another one here. I'm not real good at this. Okay, here we go. I'm now 1/10 of an inch inside of focus. Now, if you have spherical aberrations, then these guys aren't evenly spread out anymore. But I got something else. Look how this guy deviated from the line. So that means that I'm going to analyze this later, and I could be backwards for what I'm going to say now. It could be the other way, but I'm just going to say it so that it'll make sense later on when I do correct it. This guy, instead of being too far in, it was too far in and too far over, which means that the error isn't so much here, but perhaps the error is over here. And if I'm asked backwards, then the error is over here. But when I'm inside of focus, it appears that the guys run away from, okay, I'm going to analyze this because I don't know if it's a hill or a hole. Let's pretend that I know what I'm talking about for a second. If I'm on one side of focus, this guy will run downhill from a bump. And if I'm on the other side of focus, it'll run uphill from a bump. Now, we'll then be able to tell if I need to do the correction on the zone or off the zone. Like right here, my correction is on the radial. Over here, the correction is off the radial. So when I get my game on that better, I will be able to determine whether I need to run uphill or run downhill. Same with this guy over here. That guy over there. Anyway, that's where I'm at right now. I hope this video wasn't too weird. I am willing to take any critical analysis whatsoever. Okay, this is my spreadsheet or my arithmetic sheet. It's just a bunch of gobbledygook. No sense in going there. I just want people on the data display sheet. Okay, the next thing I'm going to do is I'm going to take all the arithmetic in the back and I'm going to create 8 profiles here. So it's like how you take a Mill LaCroix and you do an Euler's method to it, and you get the profile of the mirror. I'm going to do that with 8 radials over here, and I'm hoping that that will work. And I honestly don't know if it will work or not. That was kind of a weird video. I just ran through it without prepping or anything, and I hope this makes some sense, and I'm hoping that you guys like it. I'm not done. This is a work in action, but I'm hoping that this will be really useful at the Focus Hartmann test. Let me know what you think. Thanks, guys.